processing industry is one of our most important and tasteful examples of applied chemistry. For example, the processing of soda pop depends on the application of acid and base chemistry. Soda pop is a favorite drink all around the world. It's not just the taste that people love. It's the fizz and the pop that goes with it. In this program, we'll learn about the chemistry behind soda pop. We'll discover that diagnostic tests can be performed on solutions to determine if they are acidic, basic, or neutral. We'll use these tests to derive empirical definitions. We'll learn about the importance of acids and bases in a wide variety of everyday applications. We'll look at some early theories of acids and bases and see how scientific theory is revised to explain new evidence. Finally, we'll compare empirical and theoretical definitions. Right now, let's have a closer look at how this is made.
Hi, I'm here at a bottling plant with Darren, who's a senior lab technologist. Darren, what is the significance of acid-base chemistry in the beverage manufacturing process?
It's very important in the beverage process. We have water, we have syrup, we have our finished product, we have wash solutions. We need to know what the strength levels of all the various things I just described are and whether they're in spec. And the way to do that is to take known strengths of acid or bases and titrate it against it in order to determine what the concentrations or strengths are.
What about citric and phosphoric acid? What are the importance of those?
They're very important. They are key flavoring components to colas or flavored beverages. For colas, the phosphoric acid and root beers, they also have phosphoric. Those are key flavoring components that adds sort of the bite or the sharpness to it, as well as it's a limiting factor for microbial growth. So it maintains the stability of the product.
How can I tell if an acid or a base is present in this pop? Well, I guess I could read the label, but let's go to the lab instead.
Robin and I are going to perform diagnostic tests on acidic solutions and basic solutions. We will use these test results to establish an empirical definition for acid and basic solutions.
That will help me determine whether or not acids and bases are present in this beverage, right?
That's right. Now, for acidic solutions, we're going to use lemon juice, and for a basic solution, we're going to use household ammonia. Now, on the hot plate, we filled this side up with lemon juice, and we filled this side up with household ammonia. Robin, go ahead with the litmus test.
Okay, if I put red litmus in the lemon juice, it stays red. And if I put blue litmus in with the lemon juice, it turns to red.
Okay, what about the household ammonia?
I'll put red litmus in the ammonia, and it turns to blue. And blue litmus in the ammonia stays blue.
Good. All right, the next test we'll use for an indicator is bromthiamyl blue.
Okay, put a drop of bromthiamyl blue into the ammonia, and it's blue. And in the lemon juice, it's yellow.
Okay, next indicator, phenolphthalein.
Phenolphthalein is colorless in lemon juice and pink in ammonia.
All right, so we're done with these tests. Let's move on to the next set of diagnostic tests, taking the pH. All right, put the pH probe into the lemon juice. What should the range be?
It should be somewhere below 7 because it's acidic.
Right, and it is. We can see that from the meter. Rinse it off and put it into the ammonia. What should the range be?
It should be above 7.
And it is, because it's a basic solution. All right. Now, next diagnostic test is taking a look at neutralization. Acid and base solutions neutralize each other. So, let's put the probe into the lemon juice, and you can pour some household ammonia into the lemon juice. It's reading now the acid range. If we add the household ammonia, you can see that we've neutralized the solution, and now I've even gone further and changed it to the basic range. So we've neutralized the solution first. Good. Now, next test is looking at whether we can determine an acid-base property based on taste. What does lemon juice taste like?
It tastes sour.
All right. Now, how about household ammonia? What does it taste like?
I've never tasted ammonia.
It's poisonous. You wouldn't want to tasted. That's wise. Now, base solutions, if it was safe to taste, would be bitter. For example, cocoa. Baking cocoa is bitter. It is a base. There's a base component in it. Now, another property of bases that acids don't exhibit is the feel. What does soap feel like?
Slippery.
And there is a base in soap. All right, so now, when you're in the lab, even though you're sure of contents of the materials, you never want to taste anything or feel anything. And that's because common house substances can be toxic and corrosive. Okay, next test, carbonate. For our carbonate, we're going to use baking soda, sodium hydrogen carbonate. Would you add it to the lemon juice, which is our acid solution?
Okay.
What do you notice?
It's starting to bubble and fizz, so it's reacting.
All right, now add the baking soda to household ammonia. What do you notice?
Nothing's happening.
Okay, next test. We're going to take an active metal, and we'll use magnesium as our active metal. Place this active metal into our acid solution, our lemon juice. What do you notice when you put the magnesium in?
Bubbles, fizz, it looks like it's starting to react.
Good. All right, now we'll do the same thing with household ammonia. Just strip of magnesium in.
And nothing's happening.
All right, good. So now, these diagnostic tests, we can use them on your beverage. There it is. Which one will you use?
The litmus paper would probably be the easiest test.
Okay.
So,
Take a sample of your beverage, put it on the litmus paper.
okay, I'll put it onto the red litmus first. And stays pink.
Okay.
I'll put it onto the blue. If I shake the extra off, turn to pink.
Good, so we can see it's changed color, so does that confirm?
That this must have acid in it.
That's right, according to the litmus test. All right, so now we can use these diagnostic tests that we've just performed to establish this empirical definition of acid and base solutions.
You know, a sour taste may be the world's oldest indicator of acidity because acidity was first linked with the sour taste of citrus fruits. The word acid comes directly from the Latin word acidus, meaning sour.
First, Robin, let's look at the empirical definition of an acid.
Okay, aqueous acid solutions characteristically turn blue litmus red, turn bromothymol blue yellow, leave phenolphthalein colorless, have a pH less than 7, neutralize bases and taste sour, react with active metals to liberate hydrogen gas, and they react with carbonates to release carbon dioxide gas.
Next, let's look at the empirical definition of a base.
Aqueous base solutions characteristically turn red litmus blue, leave bromothymol blue blue, turn phenolphthalein pink, have a pH greater than 7, neutralize acids, taste bitter, and feel slippery.
All right, so we now have an empirical definition for acid and base solutions. But we'd like to have a look at where these acids and bases are in society. And I understand that you have a tour going. Are you ready?
I'm ready.
All right, let's go on a tour of acids and bases.
Welcome to Acidic and Basic Educational Tours. Our veteran tour guides for today's tour are Allison and Robin, and they're going to take us through an exciting journey through the world of acids and bases. And we'll start with the world of acids. Robin?
The highest volume use of an acid in industry is sulfuric acid. Many processes and products depend on it, including rubber, paint, paper manufacturing, and pharmaceuticals.
What about the products that go into our body? If I swallow one of these pills, does that mean I'm eating poisonous sulfuric acid?
No, Allison. What it means is that sulfuric acid is an intermediate chemical in the production of this pharmaceutical from its raw materials. A better example of the use of sulfuric acid in everyday life would be as a component in the solution of this battery.
Sulfuric acid is also found in acid rain. It's one of the acids that's found in rainwater, snow, and fog.
Carbonic acid is present in carbonated soft drinks. It's the carbonation that gives the fizz, right?
Right. To be more accurate, carbonic acid decomposes to water and carbon dioxide, and it's the carbon dioxide that gives the fizz.
Phosphoric acid is found in some soft drinks. It gives them a tart flavor. It also quenches thirst and acts as a preservative to extend the shelf life of the drinks.
That's right, Robin. Phosphoric acid, another exciting stop in our worldwide tour of acids.
Phosphoric acid is also used in the production of calcium dihydrogen phosphate, which is the acidic ingredient in baking powder.
The main use of phosphoric acid is in fertilizers. Plants need phosphorus as a nutrient.
Let's take a side trip to learn some more about phosphoric acid.
In the 1960s, almost all detergents contained phosphates. And that's because phosphates boosted their cleaning power.
It was discovered, however, that phosphates had a darker side. Because they acted as a fertilizer for algae in the water supply, phosphates caused eutrophication of lakes and rivers. This resulted in depletion of water's oxygen supply and destruction of the ecological balance. Since then, manufacturers of detergents have eliminated or drastically reduced the levels of phosphates in their products.
We've seen that phosphoric acid is used in the production of fertilizers, while nitric acid is also used in fertilizers, as well as in dyes and explosives. In fertilizers, nitric acid is used in the production of ammonium nitrate. Plants need nitrogen from nitrates as a nutrient. As for explosives, nitric acid is present in TNT, which stands for trinitrotoluene, and is also used by artists in etching designs and in stone lithography.
The next highlight in the world of acids is hydrochloric acid. Hydrochloric acid is mainly used in the treatment of steel and other metals to remove oxide coatings such as scale buildup in boilers. If you wanted to buy some at the hardware store, you'd find it under its commercial name, muriatic acid. It's useful for cleaning metals, masonry, cement, and stucco. It is very corrosive and must be used with great caution. Some household products also contain hydrochloric acid, like this cleaner which you use to remove the rust stain from a toilet bowl.
Hydrochloric acid is also found in your stomach. It's the acid and gastric juice secreted by your stomach and helps with protein digestion.
The acids we have seen on this tour all lack carbon, and they are called inorganic acids. But there's another type of acid that's very important, organic acids. They contain carbon. An important subgroup of these is carboxylic acids.
Here are some examples of carboxylic acids. There's ethanoic acid found in vinegar, propanoic acid found in Swiss cheese, butanoic acid, which gives us the smell of rancid butter, citric acid found in citrus fruits and some vegetables, and lactic acid, which creates the sharp taste in sour milk.
Lactic acid is an important part of our body's chemistry. When we metabolize glucose through muscular activity, lactic acid is generated in our muscles. It is usually composed into carbon dioxide and water, but with heavy exercise, it forms more rapidly, and its temporary accumulation within our muscles causes them to ache.
Our last stop in the tour of organic acids is oxalic acid. Watch out for this one. Although eating oxalic acid can be fatal, its concentration in most edible plants is probably too low to present a hazard. There's oxalic acid in spinach leaves and in the rhubarb plant. The cooked stalks of rhubarb can be eaten, but the plant's leaves contain such high concentrations of the acid that even small portions can be poisonous.
And now it's time to tour a completely new world, the world of bases. Sodium hydroxide is an important industrial chemical used in drain cleaner, oven cleaner, and it's also used to convert animal fats into soap.
And soaps have a slippery feel. And you'll remember that slippery is an empirical property of?
Bases.
You don't have to travel very far afield to find bases. Sodium bicarbonate, an ingredient in baking soda, is an example of a household base. The bicarbonate ions are not only found in baking soda, they're an important base in our blood buffering system.
Another household base with industrial applications is ammonia. Ammonia is used in the production of fertilizer, and it's also an intermediate chemical used in the production of plastics, resins, fibers, and explosives.
Magnesium hydroxide is an active ingredient in milk and magnesia, which is an antacid.
And this antacid neutralizes excess hydrochloric acid in gastric juices that can cause pain and discomfort due to acid indigestion, but it does so without interfering with normal stomach function.
What's glass doing in the world of bases? Well, the carbonate ion is a base, and so solutions of sodium carbonate, calcium carbonate, and potassium carbonate are all basic solutions. The main use of sodium carbonate in industry is in manufacturing glass.
I think you'll have to agree this tour through the world of acids and bases has been fascinating. There's still so much more to discover. Thank you for joining us on Acidic and Basic Educational Tours.
Some aqueous solutions display neither acidic properties nor basic properties. Now, Robin, you have here another kind of beverage, another aqueous solution. Let's perform some diagnostic tests on that beverage you have.
All right, I'll pour the spring water into the beakers.
Okay, now the first test we can do is litmus.
All right.
Start with the blue litmus, and I'll record the results of your test.
Okay. I'll dip a piece of the blue litmus in. And the blue litmus stays blue.
All right. Next, red litmus.
Okay. I'll put the red litmus in the spring water. And the red litmus stays red.
All right, let's go on to the pH meter. We'll take a test with that.
All right.
I'll take the meter, you take the probe, you put in your spring water.
Okay, and that's reading 6.78.
Okay. pH meter, we'll record that as 6.78. The next diagnostic test that you'll do is a reaction with an active metal, and I've got zinc there. If you want to place a piece of zinc inside your spring water,
All right.
what do you notice?
Nothing. There's no reaction.
No reaction. The next diagnostic test is with carbonates. As our carbonate sample, I have sodium hydrogen carbonate, baking soda.
Okay.
Put a little bit of that in your spring water sample.
No reaction.
No reaction. The last test on our list of diagnostic tests to perform is the taste test. Now, we won't taste here in the lab, but you had this for lunch. Was it sour or was it bitter?
It wasn't sour or bitter.
All right, so write that down. Not sour, not bitter. All right, Robin. Now, from the evidence that you've just gathered, what can you conclude?
Well, I guess we can conclude that the spring water isn't an acid or a base.
That's right.
So what would we call it then?
Well, chemists would classify these as neutral solutions. Now, there are two categories of neutral solutions: a solution of an ionic compound and a solution of a molecular compound.
So how would we be able to tell the difference between them?
Well, an ionic solution, a neutral ionic solution, is an electrolyte. An electrolyte is a solution that can conduct electricity. Now, a neutral molecular solution is a non-electrolyte. It is unable to conduct electricity in solution. Now, I've got two solutions for you here, and they have to be classified as an electrolyte or a non-electrolyte using this conductivity tester. This one here is a salt solution, sodium chloride. This one, sugar solution, sucrose. Go ahead and use the conductivity tester.
Okay, so I put this in here, the table salt solution, and I press the button, and the light blinks quickly. So I guess we can assume then that this is a conductive solution or an electrolyte.
Great, yeah. Now this one.
Okay, what's this? If I put it in the sucrose, the light isn't flashing. So that would mean that the sucrose is not an electrolyte?
Correct. Now, ionic solutions are electrolytes, but acid and base solutions are also electrolytes. So now, I have a challenge for you. Come on over here. I have 4 unidentified solutions. One is an acid solution, one is a base solution, one is neutral molecular, one solution is neutral ionic. And I want you to identify them according to the diagnostic tests we've just performed. And here are our 4 chemical labels that I'd like you to put on the beaker.
All right. First, then, I will use the conductivity meter to see which one of them does not conduct, because that would be our molecular substance, which would be our sucrose.
Okay,
So, in this one, it isn't conducting.
good. Now you can test the other 3.
All right. It conducts in this substance. It conducts here as well. And in the last one, it also conducts.
Okay, so now the first one did not conduct, it was a non-electrolyte. So that means it's a neutral molecular compound. Of these 4 labels, which one would you apply?
The sucrose.
Good. So I'll put the sucrose label in front of this beaker, our neutral molecular compound. Now we've got 3 more to test.
All right, well, if we look at the red litmus and we put a drop of each solution on it, whichever one turns it blue will be the base.
Great, go ahead.
So I put this on, and red litmus turns blue.
All right. How about the other 2?
The red litmus stays red, And with the last one, the red litmus stays red.
So, if this is then a test for a basic solution, which one of these would you pick as a label?
Sodium hydroxide.
All right, here you go. Sodium hydroxide then is identified as our basic solution. 2 more beakers to identify.
All right, well, we have blue litmus paper, so if I put a drop of an acid on there, it would turn red. So if I test each of these, whichever one turns it red will be the acid.
Correct.
And with this solution, the blue litmus turns red. And with this one, the blue litmus stays blue.
All right, so according to your diagnostic test, then this solution is an acidic solution. Which label should you apply?
The hydrochloric acid.
Good. There you go. Hydrochloric acid is our acidic solution. Leaves one solution left.
So that would have to be the sodium chloride then.
That's right, and that is our neutral ionic solution. So good. Based on these diagnostic tests, you've been able to identify these 4 unknown solutions. Good job.
The term alkaline, which we take to basic, comes from the Arabic al-kilai, meaning ashes of the saltwort plant. Cleansing abilities of alkaline solutions were known in ancient times. Saltwort plants contain high levels of sodium and potassium salts from desert soils. Camels ate this plant, and camel dung was burned as fuel. The ashes were then mixed with animal fats to produce soap. You may not be familiar with the ashes of the saltwort plant, but you can recognize this alkaline substance, soap.
Hi, Jerry.
Hi, Kathy.
What are you doing?
I'm teaching Oogie a few tricks. Here, watch this.
Okay.
Oogie, how many hydrogens in a water molecule? All right.
Wow.
Good, Oogie. Good, 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 good. Sit, stay, sit. Good, Oogie.
What
Good.
else can your dog do, Jerry?
Okay, watch this. Oogie, stand and dance. Looks like I may have to revise my theory as to how to train my dog.
I think so. I'll
Yeah.
come back when you and Oogie have got this one worked out.
Okay, see you later, Kathy.
All right, bye.
Okay, so the process I use may have to be revised to get my dog to learn the new trick. That's my theory anyway. A similar process occurs in the scientific community in developing acid-base theories. In science, no theory can be proven, but a theory can be disproved. A well-established theory may have much supporting evidence, but when conflicting evidence is found, the scientific community rejects and then replaces or revises the theory. Well, Antoine Lavoisier was one of the first to propose an acid-base theory. He proposed that oxygen is responsible for acid properties. For example, sulfuric acid contains oxygen. But evidence was later gathered to dispute his theory. It was found that not all compounds with oxygen are acids. For example, calcium oxide solution is a base. And some acids, such as hydrochloric acid, don't even contain oxygen. The theory had to be revised. Well, let's check out this book and see what it has to say about teaching Oogie the trick. All right, oh, here we go. Use lots of friendly persuasion. Well, let's try. Okay, Oogie. Oogie, I know you can do it, boy. I know you can do it. Okay, Oogie, stand and dance. Come on, Oogie. We'll have to try something different. Sir Humphrey Davy proposed the theory that hydrogen-containing compounds are acids. But eventually, scientists gathered evidence to show that many hydrogen-containing compounds, such as methane, are neutral, or others, such as ammonia, are basic. Neither of these are acid. So Davy's hydrogen theory had to be revised. Well, let's see what this book has to say. Okay, Oogie, I want you to stand up and dance. Well, Oogie, looks like it's back to the old drawing board. In 1887, Svante Arrhenius developed a theory that provided the first theoretical definition of acids and bases. His theory is still in common use today when introducing acids and bases and discussing some of their reactions. This is because parts of his theory have not been disproved. Arrhenius described acids as substances that produce hydrogen ions in aqueous solutions. and bases are substances that produce hydroxide ions in aqueous solutions. But the Arrhenius model of acids and bases is limited in that not all acids produce hydrogen ions, and not all bases produce hydroxide ions. These limitations led scientists such as Bronsted, Lowry, and Lewis to develop other theories of acid-base behavior. Scientists are always engaged in examining and testing theories. Well, let's see what this book has to say. And this theory looks good. We're going to test it. Okay, Oogie. Oogie, come. Oogie, up. Around, around, around. All right. Good job, Oogie.
Allison's going to help examine some questions about acid-base definitions. Allison, what's the main difference between the empirical definition of acids and bases and the Arrhenius definition of acids and bases?
Well, the empirical definition explains to us how the acids and bases behave, and the Arrhenius definition tells us why they behave the way they do.
Great. It's like the difference between how and why. Good. Give an example, Allison. The empirical definition tells us that acid solutions neutralize base solutions, right?
Right.
Okay. How do we know that's true?
Well, after neutralization, the pH is 7.
Good. Now, why is that true? Well, the empirical definition doesn't really tell us, does it? How about the Arrhenius definition? Well, let's take a look at it. Hydrogen ions from the acid combine with?
Hydroxide ions from the base.
Good. To form?
Neutral water molecules.
Great. And there's explanation given by the Arrhenius definition.
Right.
Good. Now, what about similarities between these two definitions?
The definitions are limited to acid and bases that are dissolved in aqueous solutions.
Right. Now, does that lead to any questions about the nature of acids and bases?
Well, can a substance be an acid or a base if it's not dissolved in an aqueous solution?
That's a really good question. Any others?
Well, can an acid or a base exist if it does not produce aqueous hydrogen or hydroxide ions?
Those are really good questions, Allison, and the answer to all those questions is yes. They can exist without those limitations, I guess you could call them. But that just goes to show that the Arrhenius definition, the Arrhenius theory of acids and bases, is a limited theory, like any theory is. And so revisions had to be made, and they have been made, and this has resulted in newer and more acceptable acid-base theories.
We began examination of acids and bases by performing diagnostic tests to define empirically what is an acid and base solution. And later on, we compared the empirical definition to Arrhenius' definition. We've seen how the internal environment of our bodies and the external environment of the world we live in depend on acids and bases. We explored the development of scientific theories in acid-base chemistry and the revision of these theories to explain new evidence. But there is still much more to learn about acids and bases. I'll leave you with these words to consider. The growth of knowledge of acids and bases is a scientific process in action. And that scientific process is the quest for knowledge, not the knowledge itself.
And now it's time to tour a completely new world, the world of bases. Sodium hydroxide is an important chemical in the industries, used in drain opener.
Drain opener. Drain opener. Open the drain!
Oogie, stand and dance.
Nothing's happened, Jerry. Jerry?
Eliminated or drastically reduced the levels of phosphates in their products.